Welcome back to my YouTube channel. We've given 9.2. These are bar with more than one diameter stepped bar. This is a stepped bar. We're still under strain. All right, we'll look under stepped bars. Talking will mean that we have two sections. We have section one. We have section one. We have section one and section. We have section one and section two. So these bars, they are placed in series. What is important again, they are in series. And then what we have learned in series is that we know that in series F1 must be equals to F2. All right, that is what we learn. And then X1 plus must be equal to the total change in length must be equal to X1 plus X2. The strain must be X1 plus X2, the total strain. So this is what is not important for you. This is what we made here. You see, they went about what is important for you is this formula, how they derived it there. Yeah, you can know that formula. There's nothing wrong there, but the simplified version, the important formula is that for you, when you're given a stepped bars, you must know that stepped bar, we're talking about the series one, right? Stepped bar, when you have given, will be mass multiplied by gravity into H plus F over E. Yang modulus must be multiplied by length of the bar 1, area of the bar 1, plus length of the second bar, the area of the bar 2. Right, this must be equals to 1 over 2 multiplied by F squared all over E into L1 over area 1 plus L2 over area 2. There, and we run out of space. That is important formula. This formula, which is important, that you're supposed to know. Right. So what you must take note is that since you've given two series, this mass, when we release this mass, will cause the extension in the second bar, which is 2 here. There will be the extension. That extension will call it X. But however, also bar 1, there will be an extension that will take place. But that extension, it's extension 2. We don't write it there. We indicate it here on the picture at the bottom. This extension actually is for the bar 1. Also will be, remember this, if this goes down, will extend. There will be extension also, because this is attached here. Even the bar 1 will have what in extension, but now the extension will write it here below because it will elongate. If this elongate will cause this will go down also, that, so we'll call it X2. That is the elongation of bar there, of the, can say X1 or X2, is up to you. You can say X1, you can choose to be here, you can choose it there. Okay, we'll elongation this, and the second elongation, this bar will come here, and that elongating of the second bar, either way. So this is what you're supposed to know. So yeah, me to put this into practical, let's say we are given now this example. This is a stepped bar. All right, this is a stepped bar anyways. So this is a stepped bar. So the question says a stepped bar shown in figure 1.11. The material of the bar should not exceed the tensile greater than that we've given the stress there greater than 80 megapascal. Determine the maximum height through which a mass of 100 kg can be allowed to fall. We want the maximum height. We want to calculate the height there. All right. So we want that hash. How can you go about that? Since it's a stepped bar, we know the equation you're supposed to use. Supposed to use the equation for stepped bar, which says that the mass will be mass multiplied by gravity into h, the one we're looking for, multiply over force over Young modulus multiplied by length 1 area 1 plus length 2 over area 2. All of these must be equals to 1 over 2 multiplied. Actually, let me just not waste time by, let me just say maths will be f squared over 2 multiplied by Young modulus. Then we have 1 over length of area 1 over area 1 plus length of part 2 over area 2. This is the formula we're supposed to use there. Alright, so this is what we're supposed to use. We want h. We want h. Alright. So are we given the mass? We've given is 100. But anyways, they will be demanded to calculate the areas. Let's just calculate the areas first so that will be easily, so that we can substitute afterwards. We know the first part there stepped is 30, the second has 20. Okay, for area 1, if we can find area 1, or let me just calculate area 1 here on the top. So area 1, we know area is pi over 4 multiplied by d squared. So pi over 4 into the diameter, 30 is the same as 0.03. We square this, will simply give us what? 706,858 times 10 to the power of minus 6 must be meter squared. Then area 2 must be pi over 4. D squared is what? Is 0.02. The diameter there, we square this. Area 2 must be 314,159 times 10 to the power of minus 6 meters squared. So we have now that the mass we are given, which is 100. We have seen that. Right here it's a mass, it's 100. Your modulus is 200. So we can go about and substitute the mass there. We need the mass. So the mass is 100 times gravity is 9.81 into the height is the one that we're looking for. The force are we given? We are not given the force, so but we've given the stress. But we know that the stress is equals to force divided by the area. If you want the force, you simply multiply with stress multiplied by the area. What is the stress? Remember, it's the same. Either way there is the same throughout, isn't it? So the stress is remember that the force will be the same either way. So So, but the maximum stress, but there they say the maximum height, we have given the expression the greater than that. So the maximum, we remember that the greatest stress will occur in the smallest bar. The maximum stress will take place here. We have given the maximum. This is the maximum stress. So is the stress for this bar, small bar, will apply in the small section, in the small cross section. So we have 8 there will take place in the small cross section, whereby the diameter of that is 20. So we'll have that our 80 times 10 to the power of 6 multiplied by the area. We've seen that was 4,159 times 10 to the power of minus 6. Then the force will be 25,133 kilonewtons. So, but we know anyways the force F1 is the same as F2. The force will be the same there. So we have that force there. Alright. The force there. (25,133) since it's kilonewton there. Is kilonewton, right? That the force is in kilonewton. So you can convert that. It's the same as times 10 to the power of positive 3. So divide by Young modulus of elasticity is 200 gigapascal into now into the length of bar 1. What is the length of bar 1? Oh, it's 1 meter. As you can see there, we have our 1 meter there. So we'll have the second one is 1.2. We have 1 meter divided by the area 1. The area, we know that it was 706,858 times 10 to the power of minus 6. We've calculated it on the top. So this is 1x1. Alright, plus the length of part 2, we have seen that it was 1.2. So this it was 1.2 into the area. The second area, here it is 301 4 is 314,159 times 10 to the power of minus 6. Alright, we have that is into this f squared there. So let me try and have some space. Let me create a little space there. Alright. Right, that is what we have. This would be equal 2 force squared there. We have our force, it was this one, 25,133 times 10 to the power of positive 3. We squared us, since you have a square, divide this by 2, multiply by Young modulus of elasticity is 200 times 10 to the power of 9 into length again, into the length 1 and area 1. So length 1, this is the same. If you can check, this is the same as that exactly. So that is the same thing. We'll have 1 over 706 like this, actually there, comma 858 times 10 to the power of minus 6 plus, I'll write here below, plus 1.2 all over 314,159 times 10 to the power of minus 6. All this. So we have to make H the subject, actually. Alright, that is the aim there, to make H the subject of the formula. So making H there, as you can see, you have to punch this on the left hand side first. Put this on the calculator, then divide by this, can get the value of H. If you do your calculation accurately, supposed to get that H will be 7,768 millimeter if you do your maths accurately. But you can manipulate the formula there. You can make H the subject. For example, there we know that you can make H the subject and substitute once, because you know that we've given mg into H plus F over E into length 1 plus area 1 plus length 2 over area 2, like this, is equals to F squared over 2 multiplied by area multiplied by Young modulus into 1 over area 1 plus area 2 over area 2. You can make the subject, divide by this, both sides, would be left with this. Making the subject of the formula F2 over 2E L1 over area 1 plus L2 over L area 2. You divide it by this, either way will be mg. This is what we have. Now we want H, so you can see this, you take all of this to the other side, you subtract by all of that. F2 over 2E into 1 into L1 plus area 1 plus L2 over area 2, divide by mg minus F, take that over E into L1 over area 1 plus L2 over area 2. This is what you have. Then you can take this as a common factor again if you want. You can take that as a common factor If you take that as a common factor, you'll have your h, this and this is the same. I want us to take that as a common factor. You're left with we have this also common. Actually, this, take this as a common fact mathematically, then we'll be left with f over e, right, into L over area 1 plus L2 over area 2. That is supposed to multiply here. Alright, like this, minus wait, here we have these two here. Okay, we have that two. Okay, let's just take that. They do not take a lot of things. You can simply take only this. You can left with that so that you cannot make a lot of things. You can still have 2 and squared. You can take out only this as a common factor. L1 over area 1 plus area 2 over area 2 into f squared over 2e minus f over e. This is a simplified form of equation. The fastest to calculate h. Just took this as a common factor, but we have this divided by the what you call the mass. So here you'll have do not forget to divide by the mass there. Only this portion, you have f squared over 2e divided by mg. Here we still have f over e. So this is the mass. This is the equation to calculate h. The shorter one, you make the subject of the formula.